In the final part of chapter 23, we're going to introduce capacitors into circuits. And we're going to start with a simple circuit that consists of a capacitor and a resistor, specifically a light bulb. So I'll take this capacitor right here, and I'll charge it up, and I'll charge it up to about 5 volts. And when I hook it up to the power supply, you can see it takes some time to charge up. And it's charged up to just about 5 volts. Now I'll take the capacitor and connect it to a light bulb. I'm going to connect it to the light bulb. And as the light bulb shines, I want you to watch 2 related phenomena. First, I want you to watch the brightness of the light bulb. Second, I want you to watch the voltage of the capacitor. So it's just shy of 5 volts. When I connect it up, the voltage drops and the light bulb dims. Now watch how much time it takes it to decrease by 1 volt. 3 to 2 to 1, 1, 2. I'm going to be hanging on for a long time if I wanted to describe it going to 0. In fact, theoretically, it never gets to 0. We have a diagram in the book that shows the voltage decrease in a circuit like this. And what you see is this. As time goes on, the rate of decrease of the voltage decreases. So it's an exponential decay that sort of slides its way into 0. And it's an exponential decay, as we saw previously when we looked at damped oscillations. But it's an exponential decay of the voltage. So I'm going to charge this capacitor back up again. So now it's charged up to 5 volts. And I'm going to hook it up not to 1 light bulb, but to 3. So I'll hook it up to 3 light bulbs connected in parallel. And as we learned in a previous segment, that means the equivalent resistance is less. So these light bulbs will draw more current. Now I want you to think about this. What is going to happen to the time that it takes for the capacitor to discharge with 3 light bulbs as opposed to 1? How will the time for the discharge compare? We'll give you some choices. Now think about this. I've got 3 light bulbs that draw more current, which means more charge flows out of the capacitor. And so if more charge flows out of the capacitor, what that means is it'll discharge more rapidly. And we can see that if I hook up these light bulbs. Watch the brightness decrease, watch the voltage decrease. And with 3 light bulbs, it drops much more rapidly, 2 to 1, much more quickly, much more quickly. So when I have a capacitor in a circuit, I have the capacity to do timing, okay? By having more light bulbs, by having less resistance, I have a quicker discharge. And in fact, we can take a circuit that consists of a capacitor and a resistor, an RC circuit, and we can associate with it a time constant that is a measure of how long it takes the capacitor to discharge, or how long it takes the capacitor to charge. That's the other piece of the puzzle. But we have a timing element in the circuit, and that's going to be a really, really important thing, and there's lots of circuits that depend upon that. If I vary the resistance, I vary the time constant, and so I can vary the time. Now this circuit right here is a little neon light bulb flasher, and what happens is this. There's a capacitor that charges up through a resistor, and as it charges up, it reaches a certain voltage. When the voltage is big enough to light the neon light bulb lights. But then that discharges the capacitor. Then the process starts again, and the capacitor has to charge back up again, and it's charged through a resistor. So it's an RC circuit, but it's an RC circuit for charging. Now I'm going to take this 1 mega ohm resistor in this circuit and replace it by a 5 mega ohm resistor in the circuit. Now look at the flash rate of this circuit. And that is a measure of the time constant of the circuit, okay? Bigger time constant, there's going to be a bigger time between flashes because it will take longer to charge. I'm going to take this 1 mega ohm resistor and switch it for a 5 mega ohm resistor. How will that change the flash rate of the neon light bulb? We'll give you some choices. Well, if I have a 5 mega ohm resistor, the time constant is bigger by a factor of 5. So it's going to take more time to charge up. And if it takes more time to charge up, there's going to be more time between flashes. And so now the time between flashes of the bulbs is perceptibly longer. There it goes. And it won't go again for a while. So I have a much, much longer time constant, and so a much, much longer time between flashes. But the mathematics of the RC circuit and the timing features associated with it are connected to something else. In the book, we present a model of electric conduction in the nervous system, modeling it as a series of RC circuits. And the conduction of nerve impulses to muscles is an electrical signal. And when muscles contract, they too make an electrical signal by depolarizing cell membranes. And we talk about all this in chapter 23. And we use RC circuits, these circuits of resistors and capacitors, to model them. And we want to close with a quick demonstration of a measurement of the voltages that are produced when muscle cells depolarize. So muscle and nerve cells have an electrical nature, and you have a difference in potential between the inside and the outside of a cell. When a cell depolarizes, and that means when a nerve cell is transmitting a signal, when a muscle cell is contracting, I have a depolarization that changes the polarization between the inside and the outside. That's how nerve cells transmit signals. It's how muscle cells contract. When I squeeze my fingers together, nerves transmit signals that muscle cells are to contract, and when they contract, they depolarize, and so they make a small potential difference. And this potential difference is picked up and amplified, and that's the sound that you hear. So it's a wonderful connection between the worlds of physics and the world of biology.